Okay, let us continue with the last part of the question where we needed to find a dense subset. So, so the question is to find the dense subset of this space, a dense subset of this set. But we're gonna find a dense subspace instead of subset. We're not just gonna find a subset, but a subspace. So we have some tasks to do to achieve this. The first task is to define that set. So to define that set, which is gonna be the a subspace of this of our set of our space, and we see if it's gonna be dense on in in LP. So the first thing that we do, we define this set. We define f of n, calligraphic f of n, as this set, the set of this kind of particular sequences like x1, a sequences that has as element x1, x2 up to xn that are eventually non-zero, and after xn you have zero everywhere. So you have a sequence like this. So it's like a finite sequence, uh, a sequence with only finite non-zero term, and taken in this order. So we start by x1 up to xn successively, eventually non-zero element, and then after that zero everywhere. So that's why we say n is an integer, and the xk, all the xk, oh, I'm sorry, all the xk are in R for all n, and for all k between 1 and n. So all the xk are in R for all k between 1 and n. Since this is our set f1 and n, f1 of n, so calligraphic f of n. So we must prove that this set that we define here is a subset, first of all, is a subset of LP. This is very clear, right? LP is a set of sequences like xn that are such that if you sum xn to the power p, you get a number that is certainly less than plus infinity for n from 1 to plus infinity. So now in our case, if we consider element of f1 of f1 of n, those are just, you have x1, x2 up to xn. It is a finite number. You only have a finite number of non-zero and infinitely many zeros. So if you sum this term, you're just gonna get, or write it k, you're just gonna get the absolute value of x1 to the power p, plus you continue like that, and you end at the absolute value of xn to the power p. So all those are real numbers. So it's a finite sum of real numbers. It cannot be anything but a number that is then strictly less than plus infinity. That is why you see that all the elements of this form that forms the set calligraphic f of n are also LP elements. So that makes this set a subset of the LP space. So because we wanted to prove that it is not only a subset, but it is actually a subspace, we must now prove that this is a vector space, subspace of LP. So how to prove it? You only need to prove that if you take two elements of this, the sum of those two elements is going to be an element of F1. And if you take an element of F1, you multiply it by a scalar number, a scalar, you will get another element of F1. So to do it, you only need to show that if you take two elements, X and Y, in F1, and you take two number, alpha and beta, in F1, that can be R or C, But in our case, we only consider R because you see, we don't care about the case of C. That will be like this. If you take this linear combination of x and y with this scalar alpha and beta, we will always get an element. Oh, I'm sorry. This is like 0, and you can change an element of this calligraphic f. So compute this. This is just this alpha x1 plus beta y1, and you continue like this, alpha r plus beta r, and then you continue gamma z r plus 1, gamma up to gamma zq, and 0 everywhere for the remaining. Where r is what? The minimum between n1 and n2. n1 is the number of non-zero terms of x. n2 is the number of non-zero terms of y. So if you add them in this order, you're just gonna add this and this, this and this, up to the minimum between them. That's what we call R. You do the adding. But when you reach the minimum, it means that the other sequence, one between x and y, has become 0. So we will only have one term in the summation. So that's why here we turn that remaining term to z, and between alpha and beta, one of them will not appear. So the one that's going to appear, we call it gamma. That is what we say here. So Q is the maximum between n1 and n2, and the gamma is the number that correspond that remain. If your minimum is n2, it means that at this point n2 has disappeared, n2 has disappeared, so you only remain with alpha. So your gamma will be alpha, and z also the same thing as gamma, so the same as here. So when your minimum is n1, at this point you have finished with x, then you start writing only y. So your gamma is going to be beta, and the z also is going to be the z r plus 1 is going to be the same thing as this one. So you see that we will only have eventually finite number of non-zero after this q. All the remaining term are going to be 0, 0, 0 ever. So we're going to still be an element of f1 of n. So in this way, we see that f1 is stable with the usual operation in LP, the addition and the scalar multiplication. So that makes f1 of n in subspace of LP. So now the difficult part was to prove that this is actually dense in LP. To do this, you need to prove that for every x in LP, for every sequence x in LP whose component are x1, x2, x3, x4 up to x infinity that we're not gonna reach in LP, we can always find a sequence. You have, this is an element which is a sequence. This is an element x in LP, but we know that element of x in LP are sequences. So now we must find a sequence of element of F1. But element of F1 are themselves sequences. So it means that if I get xm here in F1 of n, this xm is a sequence. It must have a component. It must have components like xm1, xm2, like this, up to xm. I don't know where I'm gonna stop. Let's call it q, and 0, 0 everywhere according to the way we defined f1 of n. So that is what we must find, we must do. So the result is that we must always find a sequence here that converges to x. Converging to x means this. Let me write it in the LP with respect to LP. I can put p to the power p here, the same. To the power is the same. So that is what we must do. We must find the sequence. So let us then take this, an element x in LP, and define this element x1, which has only one component that is eventually non-zero and zero everywhere. But this one component comes from x. So the first component of x. You define the element x2 as the first two elements of x, two components of x, x1 and x2, and everywhere 0. We define x2 as x1, x2, and x3 that you took from x, and the remaining part 0, 0, 0 everywhere. So if you continue like this, in general, you can define this element xn, x to the power n out of the bracket, to be x1, x2, x3 up to xm, and a 0 everywhere. For all m, you can do it. So this will give you elements of this set f1 of m that we call x to the power m for all n. Then we have a sequence. This is a sequence. This is a sequence in this set. But you see the element of this sequence, those of element of this sequence that are called x to the power m are also sequences. So now we need to compute this and to see if its limit is 0. First, what is this? We must know what is this subtraction. Let us compute it. Xm minus x is, you write xm is this, and x is this. So xm has a 0, 0, 0 everywhere from m1, xm plus 1. But xn doesn't need to have this property. So it is x1, x2, x0 up to x infinity. We don't know x infinity. So if we do the subtraction, we're gonna get those two that are going to cancel out. This are gonna cancel out. This is gonna cancel out this. You only remain with this. So you have minus x m plus 1, minus x m plus 2, and etc. etc. So now, if we call this z. Z is a vector whose first component are 0, 0, 0 up to m plus 1, and up to m. And from m plus 1, you have minus x, m plus 1 up to x. So you can come back to x. So if we compute this norm, what we wanted, it's like we want to compute the LP norm of Z, which has as definition this. And when we write the definition, we're going to see that the first component up to xm are going to be 0, 0, 0. They are absolute value to 0. Our p is 0. And then the rest are just the summation, the normal summation as we know it. So when we're going to come back to the definition of z, so you're going to get minus xm to the power p up to probably go back. So then if you write it, we write it like this, that we can write in a condensed form as this. In a short form of this, as the summation for k going from 1 to plus infinity of the absolute value of xm to plus k to the power p in absolute value. So then, but this you can write it as you have summation from 1 to plus infinity, where you subtract the summation from 1 to m, and so it's in order to remain only with this term. So this is what we do here. But when you write it like this, you remember that this first term gives you the LP norm of x to the power p. But the rest, you can just write it like this. And then, when you will compute this, you get the LP norm of x to the power p minus this term. But when you compute the limit as m goes to plus infinity of this term, this is the summation for k going from 1 to plus infinity of what? Of xk to the power p, which is again the LP norm of x to the power p. So then the limit of this is the LP norm of x to the power p minus the LP norm of x to the power p, which is 0. So it means that the sequence that we built converge to to x with respect to the LP norm. This is what we needed. We have seen that for all x in LP, LP we wrote it like this. We have found a sequence of elements in f round of n such that this sequence xm converges to x. This is with respect to LP, to the LP norm. This is the condition to say that this space f1 of n is dense in LP of n. So this because it is a subspace of L, we can call it now F1 is a dense subspace of LP. This is what we needed to do to prove our results. And I'm advising you are following me. Don't forget to share this video, especially to people who know that you know who can speak Lingala, was my local language, so as they can subscribe to my channel and continue to be like uh, notified for any new video that's gonna be published. Thank you very much for following.